part 8.4, variable size reduction. So in this part, we study another special case. We do the recursion. When we use recursion to reduce the problem size reduction not fixed. The size is reduced in a variable way. So let us look at the problem first. Example. Problem number 9, greatest common divisor. We're familiar with this concept. So let us look at the question. Given two non-negative integers m and n, not both 0. Our goal, find their greatest common divisor, GCD of m and n. To solve this problem, we have some experience. If you recall your high school experience or middle school, probably not high school, middle school, probably you can solve this kind of problem. The basic procedure like this. All right. Step 1, find the prime factorization of m. Okay. Step 2, find the prime factorization of n. Step 3, find all the common prime factors. All right. Step 4, compute the product of all the common prime factors. Very simple, right? Let us use a simple example to go through all these steps. GCD of 60 and 24. So we do prime factorization of 60, so we get this simple factorization. 24, 2 squared, 2 cubed times 3. Then look at the prime factor 2, the largest possible power of 2 that both numbers have as a factor, 2 squared. For 3, just the 3, right? 5, it's not common. It's a not common prime factor, so we drop it. So the answer, 2 squared times 3 equals 12. So we get the answer GCD of 60 and 24 equals 12. All right. So that's the solution, right? It looks pretty good, right? Nothing is wrong, right? We will look at this question later, because we will use another way to solve it. After that, we can compare these two different ways, which one is clearly better. First, we notice the main property of this method. So this method relies on prime factorization. So this is the key property of this method, prime factorization. All right, so let us just leave there. Next, we want to look at the problem size. How do we define the problem size for this problem? First, assumption. Based on the assumption we have, we do not allow both integers equal to 0. So when n equals 0, m cannot be 0, right? So non-negative integer, but not both 0. So one of the two given integers cannot be 0. Then, when we look at the problem size, first we have the simple fact, maximum of m and n not equal to 0. Okay, we know the maximum of these two numbers not equal to 0. Then we can answer this question, what is the problem size of this GCD problem? The answer is maximum of the two given integers. Maximum. All right, the problem size. All right? Yeah. Because that's the most straightforward way to describe that problem. All right? Yeah. Question. How do we reduce the problem size? How do we reduce the problem size? All right? Yeah. Recursion. All right? Yeah. That is common way in problem solving. Problem size reduction. Yeah. So next, we need to answer this question. Yeah. All right. So, but when we do problem size reduction, we need to use some mathematical tool. Yeah. Here, there is a simple but important tool we need to use. Division algorithm. So what is division algorithm? Yeah. You know how to do integer division, right? Yeah. Here, we just write integer division in a formal way. Yeah. So then we can use it as a formula. Yeah. Given positive integers a and b not equal to 0, because we want to use b as the divisor, so the divisor cannot be the 0. Yeah. Then there exists unique integers q and r. Q for quotient, r for the remainder. Yeah. Unique q and r. Yeah. With this inequality, 0 less than or equal to r, strictly less than the divisor b. Yeah. Such that we have this representation. A equals b times q plus r. Pretty easy, right? Yeah. But this simple method, algorithm, we call very important in solving this GCD problem. Otherwise, we don't know how to solve it. Using problem size reduction. Yeah. Our goal, we want to do problem size reduction. Yeah. So this method or this tool is critical to do the problem size reduction. Yeah. All right, so let us do the implementation. Yeah. For convenience, we assume m greater or equal to n and greater than 0 for convenience. Okay, so then when we go back to our division algorithm, a corresponds to m, b corresponds to n. So then we can find the remainder r in this range greater or equal to 0, strictly less than n. Strictly less than n. So this part is important because the remainder is always less than the divisor. So that makes sure we can reduce the problem size in this way. Yeah. All right, so let us look at the details. Now we have m equals n times q plus r. Yeah. All right, so that's our starting formula. After that, we need to explore some key property for problem size reduction. Yeah. How do we do it? Through transformation. Transformation. What kind of transformation? Formula transformation. Yeah. Look at this. Yeah. When we write GCD of m and n, we want to do some equivalent expression for this one. Yeah. All right, so we replace m by nq plus r here. When we do this replacement, we want to simplify the expression. Yeah. All right, before we do the simplification, let us look at this transformation. All right, when you look at m over n, that fraction, you can write it as q integer plus another fraction R over N. That's simple, right? Yeah. From here, you can easily get this new transformation. Okay, so you can easily get that. All right, yeah, here, this formula. Okay, you can easily get that. Yeah. And here, another important thing we want to see from this new expression, new equality. Yeah. Can you see the greatest common divisor of M and N equals the greatest common divisor of R and N? Can you see that? Yeah, because the integer part does not impact the greatest common divisor of the numerator and the denominator. Integer, right? Integer part, no impact. Okay, all right. So that's one way, yeah. Because you can understand in this way. When you simplify the fraction at the left-hand side, M and N, by crossing out the greatest common divisor, right? You can do the cancellation, cross out greatest common divisor. That same divisor can also be crossed out at the right-hand side, right? You know, not the whole thing. That divisor can be crossed out from the numerator, denominator at the right-hand side fraction, right? Yeah. Because after simplification, the denominator of both sides should be the same, right? Yeah. That's pretty obvious. Yeah. So with this kind of view analysis, yeah, so we have the conclusion. GCD of the two fractions of that equality should be the same. That is our key property. So we can cross out NQ part. No impact, no inference, right? Yeah. So the result, GCD of M and N equals GCD of N and R. This gives us the concrete problem size reduction. Yep. Because in this new expression, the problem size is reduced. Okay, yeah. And you can see the problem size is reduced in a variable way. Variable, not a fixed way, variable way. Okay, yeah. So with this key property, we can do problem size reduction again and again until the problem size cannot be reduced and we get the answer. That's the idea. The idea of the new method. All right, so based on this new idea, so let us do a simple calculation of our previous example, the same example, GCD of 60 and 24. Yeah. Here you see a sequence of problem size reduction. Yeah. To see that, we just write 60 equals 2 times 24 plus 12, remainder 12. We know the quotient multiple of divisor, that term can be crossed out, and we can update the GCD expression. So the second GCD expression is GCD of 24 and 12. And we know 24 is a multiple of 12, so the answer is 12. All right? Yep. So this is a completely new method, right? Yep. All right. Next, we want to look at the implementation. Yeah. So we have this idea, yeah, how to solve the problem. Now we need to write a formula, write a code. All right. To write a formula, here we have this famous Euclid's algorithm. Euclid's algorithm, very famous. Yeah. It has history more than 2,000 years. That old. Yeah. All right. So the rule is like this. When we calculate GCD of x and y, we have three cases. The first case, when y equals 0, the answer is x, but we should make sure x not equal to 0. All right. The second case, when x mod y equals 0, we know for this situation, y cannot be 0. So x mod non-zero y equals 0, then the answer is y. Yeah. So two simple special cases. All right. So then the remaining regular case, yeah, then recursion, problem size reduction, GCD of y comma x mod y, remainder x percent sign mod y. All right, yeah, that's simple. That's the Nucleus algorithm. Yeah, if we write a, yeah, so he, yeah, all right, yeah, you can easily see the problem size reduction when you use this formula. All right, and finally, the code implementation. You can define an integer function, GCD, yeah, and when you define, you consider 4 cases, not 3, because the first case, you need to consider both given integers are 0. In that situation, GCD not well defined, so you return -1. When people get a -1 answer, they know not defined, GCD. Other than that, then 3 cases we have seen. So the first one, return x. Second one, return y. And the last one, recursion. Yeah. So that's the simple solution. All right? Okay, yeah. Now, at the end, finally, all right, we do some conclusion at the end. We need to compare 2 methods, right? We have the method 1, prime factorization based solution. Method 2, recursion based solution. Now, first, let me ask you this question. Which one is better? Which one is better? Think a little bit. Which one is clearly better? You may not get a simple answer, because if you just want to base on the 2 examples we have, it may not be that easy. It may not be that easy to get the answer. Here, let me give you some critical background knowledge. After you have that critical background knowledge, then you can get the answer easily. So what's that critical background knowledge? Do prime factorization, right? Prime factorization. Let's look at this issue first. Method 1 relies on this operation. Yeah, let's treat it as an operation. The question is how hard it is. How hard to do prime factorization. All right? Yeah. How hard when I ask you this question, when and the given integer to be factorized, when m is very large. All right, under this situation, how hard is prime factorization? N is very large. Okay. How large? So here, let me give you some idea. Think about n has 1,000 digits. Is that large? 1,000 digits. Okay? If you feel that is not large enough, think about when n has 1 million digits. Is that large? Digits. Okay? 1 million digits. That number. Now I ask you to do the prime factorization. How hard it is. Think about it. Okay? Even if you use the most powerful computer in the world, it is still extremely slow. Extremely slow. Okay? How to get that idea about how slow it is? How do you get idea? In years. Here, let me just roughly, give you some estimate. Roughly, in years, the most powerful computer in the world, if you want to calculate the prime factorization on a huge integer, how big? You can think about millions of digits. That huge. You need to spend years, several years, to get an answer. That's the background we need to have. Okay, background we need to have. All right. Now, with that background, which two methods is better? Method 1, method 2. Clearly, method 1 is not good, because when you find a GCD of two huge integers, both million digits, all right, both millions of digits, then nobody can wait for many years, right? Yeah. If we switch to method number 2, basically we do integer division. When we do integer division, even huge numbers, it's pretty fast. Very fast. Integer division could be very, very fast. All right? So then, size reduction, several times, although many times, but your algorithm is still extremely fast. So clearly, method number 2 is much faster. It does not rely on prime factorization, right? You don't need to do prime factorization. You just do integer division. For integer division is fast. Even for huge integers, it is still very fast. So the answer, you can get it much faster. All right? Yeah. So the conclusion, the method should avoid prime factorization. Right? Yeah. That's our conclusion. Okay? All right. Yeah. So that is our last video of part A of module 3. Yeah. And then after this question, I like to give our project number 2 based on this problem. Definitely we need to use method number 2. Okay? We need to use method number 2. All right? Yeah. Yeah, but this project number 2, yeah, let me think about it. Yeah, because for this one, if you use prime factorization, it could be very slow. Okay? It could be very slow. Yeah. So this is possible idea. Okay? Yeah. Let me say just possible idea. Although it's a good project. Okay? Possible idea. Yeah. But the main thing is I need to see how hard for the prime factorization part. Yeah. If it is too hard, so I may like to give that as your optional project, okay, for extra credit. Yeah, for extra credit. The regular project, I may use another question, another problem. All right. Yeah. So this, it's a good option for optional project. Optional project for extra credit. Okay. So that is some good chance for you. All right. So let us finish this video right here.